So let's get started with lecture today. Before I actually get started, a couple of announcements. As you probably know, your midterm is tonight from 7 to 9 p.m. It's not about circuits, it's about linear algebra. This lecture is about circuits. See Piazza for details. If I announce the details in lecture, I'm almost certain to get them wrong. So just check the Piazza post. It has all the information that you need. And another friendly reminder that homework 4 is due on Sunday. How many of you guys have looked at homework 4? Yeah, almost nobody. Well, good for you for looking at it. It's a good one, good practice. All right, so let's just do a quick recap of last lecture. So the four main things that we did in last lecture were putting a whole bunch of resistors in series, putting a bunch of resistors in parallel, and very briefly we looked at voltage dividers, and current dividers. Okay, are there any questions on these? Any issues from last time? I know I did voltage dividers pretty quickly at the end of last lecture, as well as current dividers. Everybody okay with it? Yeah.
Wait, so voltage dividers are the series, right?
That's right, yeah. So if you put two resistors in series, the voltage across them will be divided on each resistor, okay? So there's one thing I want to do, which is the same thing, make it really big. That current divider, except instead of with resistances, I want to solve the same circuit with conductance instead. Okay? I want to see how this current divides and what the equivalent conductance is. All right? Is this clear, what I want to do exactly here? All right, so in each one of these branches, I have some voltage, V1 and V2, which, as we saw from last time, are actually the same, right? And we also have some current, IG1, histogram, IG2. Okay, and we want to solve for these currents, and in the end, determine how we can actually put these two conductances together. Okay? Clear? So I know V1 is equal to V2 is equal to whatever source voltage is being generated by this current source, right? All the voltages are the same. They're all in parallel. Okay? Now, what is the current through this first conductor, given the conductance and, let's just say I know the voltage right now? Does anybody remember what the definition of conductance is? What is conductance? 1 over R, yeah. It's just 1 over the resistance. So what's Ohm's law for a conductor? It's the same as Ohm's law for a resistor, but with 1 over R, right? Okay. So before Ohm's law, V equals IR, okay? Or I is equal to V times G, voltage times conductance, right? Okay? So I can do that here. And I'm going to do the same thing for the other one. Clear to everybody? It's almost the exact same procedure that I did for the last one, right? Now I know that the total current, if I do KCL, here I've got a current IS. The total current, IS, is equal to IG1 plus IG2, which is the voltage times G1 plus G2. So what is the equivalent conductance of these two? Yeah. GEQ, equivalent conductance, is just this term right here. Okay? So just quickly to get back to our recap, series resistance, resistors add in series. Oh, I ran out of room. Resistors add in series. Conductances, let me just write G. G's add. Okay? So if I rewrite my expressions, if I rewrite my resistances as conductances, they add in shunt or in parallel. Okay? This clear to everybody? Good. Another circuit that I want to go over again is this voltage divider that I used earlier. But this time, I want to use it for some purpose. I want this to actually do something for me. So let's imagine, you have a question in the back there? No. Let's imagine that this source voltage is actually a signal, like a sound signal, something like after I transduce my voice into this microphone, something like that, a voltage that's proportional to what I'm saying, let's say. And it's too loud. So what I want to do is I want to reduce it. I want to divide it down, okay? And so we already found that last time, if I've got some resistors R1 and R2, the voltage across R2 here, I'm going to call that V out, is equal to R2 over R1 plus R2 times my source voltage Vs. Now just a quick question for you. What's the voltage across R1 if I define that like this? What is this voltage right here? Yeah. The answer was it's R1 over R1 plus R2 times Vs. Okay, and that should be clear for two reasons. One, if I took this resistor R1 and I moved it below R2 in my schematic, it wouldn't change my schematic at all, right? So you can think about it that way, potentially. If I just switched this order, the voltage divider would then be across R1. Wouldn't change anything, right? My expression would be the same. The other way of looking at it is the sum VR1 plus VR2, or V out in this case, has to be equal to Vs. And is that true here? Yes, right? R1 plus R2, the fractions are the same. You get 1 times Vs. Okay, great. All right, so we satisfy KCL. Or KVL, excuse me. But what happens now if I take this voltage and I do what's called loading it? I'm going to put a resistor here in parallel with my voltage divider, and I'm going to call this R speaker. So that's an equivalent resistance of my speaker, let's say. So again, just our little example, this was a sound, If you're listening to music or something, it's too loud, you want to divide the signal down, you want to reduce the voltage, but now I have to drive my speaker. Now, does this expression for V out, does it apply anymore?
No.
It's not right, right? Is it clear to everybody why? Now I have a new resistance. So I'm going to draw that real quick. Oh, let's do it over there. Hold on. So I'm going to draw an equivalent circuit here. Where this is still R1, just like it was before. This voltage is still Vs, just like it was before. But this now, this new resistor, here's my voltage, V out new, and I've got some R new. Now what is R new? Anybody know? Yeah?
It's the equivalent to R all for the parallel.
It's the equivalent R of the parallel combination. So it's the parallel combination of R speaker and R2. Okay? And so if we remember from last time, or R2, yeah, R2, not R new. R2 parallel R speaker. Okay? Which, if we want to write it out explicitly, it's either R2 R speaker over R2 plus R speaker, or 1 over R2 plus 1 over R speaker. Okay, these are all equivalent expressions. Those two lines are just a shorthand notation. Now, what can you say about R new and the resistances R speaker and R2? Who thinks that the new equivalent parallel resistance is greater than one of those two resistors? Nobody. Well, that's good, because it's actually less. It must be less strictly than R2 or R speaker. It is less than this. It is less than the smaller of the two. It must be. Okay? Which means that my new resistance here is less than it was before. Which means what about my new voltage? It's less, right? From the voltage division formula. Okay? Is this clear to everybody? That means that when I put my speaker, the thing that's actually creating the sound, in this case, by loading my circuit, I've changed the voltage now, and I've further lowered it. Maybe more than I wanted to, right? So let's give some numbers here. So let's say, just for example, our speaker is 8 ohms. Well, let's make it 10, just nice even number. 10 ohms, okay, which is not an atypical resistance for a speaker. If R1 and R2 are both equal to 1 kilo ohm, what's V out going to be? I'm going to get the curly V. Let's say approximately. What is it going to be? engineering approximation? Well, first off, what's my expression now? It's the source voltage times R nu over R nu plus R1, where R nu again is the parallel combination of the speaker and R2. Clear? So what's R nu? If I tell you R2 is 1 kilo ohm, our speaker is 10 ohms, it'll be a little bit less than 10 ohms, right? So it's approximately, so this is strictly equal. This is approximately Vs times 10 ohms about divided by 10 plus 1,000, which is pretty close to 0. So I've taken my circuit. I wanted to divide my signal by 2, and instead I just got rid of it entirely. There's no signal. I can't hear anything. So what do I have to do? What do I have to do with my resistors R1 and R2 if I want this circuit to work? I want to divide by 2. That's my goal. Suppose. I heard it. Somebody said it. They said, I don't know who it was, they said decrease the resistance. So I take these R1 and R2, and I have to make them smaller. In fact, I have to make them much smaller, comparatively, than my speaker resistance, right? So if I do it again, and I say instead, our speaker is still 10 ohms, now R1 and R2 are 1 milliohm. Really small. Now what's V out? Again. This expression still applies. Now what's my R nu approximately? That new parallel equivalent resistance. It's about 1 milliohm, right? Yeah. Times. Sorry. So I did it, right? Yes?
Could you have also increased the resistance of the speaker?
Could I also sorry, let me repeat your question. Could I also have increased the resistance of the speaker? The answer is probably not, okay? So this is just some item that I'm given, and I have to be able to provide it a voltage. Yes, you can choose between different speakers, but more likely than not, it'll be somewhere around 10 ohms, right? 8 ohms, 4 ohms, something like that. Good question, though. Okay, now what's the downside of using, yes?
Oh, wait, you mean like there is it R2, R1 equal to 1 milliohm?
Yes, R2 and R1 are each equal to 1 milliohm, so that's 1/1000th of a...
It becomes 1 milliohm plus 1 milliohm.
So remember that when I have parallel resistances, it's equivalent to, let's see, I've got it over here.
Equivalent to R1 plus like something like R nu plus R1, but like R nu is like 10 ohms.
So when I put two resistors in parallel, it must be less than the smaller of the two. And in fact, when I have parallel combinations where one resistor is much, much larger than the other, it ends up being very close to the smaller resistance. Okay? Maybe you'll get some practice on the homework, and that'll be more clear probably. Okay? Any other questions on this? Now, what's the downside of using 1 milliohm resistors? Practically. I heard something. They'll explode? Is that what you said? I mean, that's certainly possible. How much power am I dumping in this if my speaker voltage, let's say it's 5 volts? So this Vs, so R1, R2 is 1 milliohm. V source, let's say, is 1 volt. How much power is being dissipated in, let's say, R1? So what's power? It's the current times the voltage in the resistor, right? Which is equivalent to, for a resistor, the voltage across the resistor squared divided by the resistance. And you can get this from Ohm's law, right? V equals IR. I just do a little substitution. That's it. Is this clear to everybody, this step that I just did? So in this circuit, for these numbers, what's the voltage across this resistor R1? I just want the power in this resistor. PR1, current in R1, voltage in R1, voltage across R1. What is that? Just the voltage for now. Somebody's going to have to speak up. Half of Vs. Which in this case is 1 volt, just to give it a number. And the resistance is 1 milliohm. I'll put the units here. Half a volt divided by a milliohm, which is 250 watts. That is a lot of power, like really a lot, okay? Your resistors that you have in your lab kit that we give you are rated for 1/4 of 1 watt, meaning if you put more than 1/4 of 1 watt through it, it will explode. Like you'll see it get charred. And I mean, okay, it won't like explode, but it'll melt. Please don't do that. Right, so this is the downside, right? The price that I paid for being able to divide this voltage by 2 with a small load resistance, meaning my speaker, is power, okay? And we'll see in about a week how we can deal with that without this voltage divider circuit. There's actually a better way of doing it, okay? But this is basically an example of how we can use our knowledge of voltage dividers, parallel equivalent resistances to solve a circuit like this, okay? Cool. Let's do one more example, just so we can sort of flex our circuit analysis muscles a little bit. This clear to everybody? What I've done so far? Nothing too special. I'm going to do the following. I'm going to give you this circuit. Got a voltage source. Let me draw it lower. Now just a quick note about grounds here. So ground, if I have a ground in a circuit, it's implied that all of the grounds are connected together. Okay, so what I didn't draw, because it makes my pretty circuit a little ugly, is this implied connection between these two. Okay? Any question? Yes, you have a question? What happens if they're not connected? So then you have issues with, so in a real circuit, you wouldn't have a return path in your circuit. So if we think about, let's think about KCL for a second. Let's say I didn't ground that node. This is a good question, by the way. Would there be any current in my circuit? No, right? Because if we look at this node over here, there cannot be any current, right? Great question. So we have to create a return path for our current. Okay? Is the question and answer clear to everybody? Right, so this connection is implied. I'm going to say I've got some voltage V source, and I have R1, R2, R3, R4, and R5. And I say I want to know all the currents and all the voltages in this circuit. Why? I don't know. But I'm telling you that I want it, okay? Now, yes, you could say, okay, this circuit is too much. There's a lot going on here. Do nodal analysis, okay? If you're not comfortable with this parallel series equivalence, the voltage dividers, current dividers, it's okay, right? Nodal analysis is fine. There's nothing wrong with it. It just takes a longer time, okay? And the other thing is you kind of lose intuition for the circuit. So like over here, when we solved this circuit using parallel series equivalence and voltage division, we sort of had an intuition, right? We understood what was going on in the circuit. With nodal analysis, you kind of lose that because it's so mechanical, it's so methodical. Cool, so now let's solve this circuit. Anyone have an idea of how we're going to do this? Where do we even start? Yeah, let's do that. First, let's find the equivalent resistance for the parallel resistors. And redraw our circuit. So the voltage source Vs, that stays the same. And now we have this first one. I'm going to take those two resistors, put them together. Let's call that RP1. I've still got R3 right here. That one's unchanged. Right? There's nothing in parallel with RP1 or with R3. And then let's call this one RP2. And this is ground, right? Implied connection, still there. Okay, for this circuit, what are RP1 and RP2? I know you know. Yeah.
RP1 is just R1 times R2 over R1 plus R2.
Yep, it's just the parallel combination of R1 and R2, right? So I'm going to write it shorthand. For each one of these. Just the parallel combination. Now, what information did I lose from my original circuit when I did this? The branch current through each one of those two resistors, okay? I don't have that information anymore because I simplified my circuit. Great, now what? That was a good start. What can I do now? Yeah. Sure, I certainly could. So let's do another simplification. Voltage source is still the same as my ground connection. And now I have one resistor. I'm going to call that R total, RTOT, which is just the series combination. As we know from last lecture, resistors add in series. So we've got RP1, RP2, and R3, which is just hanging out from before. Okay? Clear? Great. Now what? Okay, now we've simplified our circuit to a voltage source and a resistor. What can we do now? Yeah? Use Ohm's law. Yeah, let's use Ohm's law. So what's the current? Call it I source. It's just the voltage, V source, divided by this total resistance, RP1 plus RP2 plus R3. Okay? Now in our original circuit, let's go back to that one. Where's IS? What does that mean? You got again?
IS is going to be the current flowing into the first parallel combination of resistors.
Yep. IS is still the current flowing out of this current source, or the voltage source, excuse me. Okay? So I know what that is now. Let's say all these resistors and all the voltages are given. I now know this current, IS. Can I very quickly from this find all of the currents in the circuit? How? It's just a bunch of current dividers, right? IS has to split this way. Let me draw it in blue because I have my blue one. Can everybody see the blue? Oh, it's very nice. I've got some IR1 and IR2, and I know IR1 plus IR2 is equal to IS from Kirchhoff's law, current law. Okay, and I know the formula, right? I didn't actually write it up, did I? The current division formula, right? It's going to go proportional to the other resistance. So this current will be R2 over R1 plus R2 times the source current, and I'm going to write this in a second. And the other one will be the difference, R1 over R1 plus R2. Okay? What about this current? IR3.
Same as IS.
It's just IS, right? So let's summarize this. I've got IR1, IR2, 3, 4, and 5. IR1 is just the current division formula, right? So it's R2, R1 plus R2 times IS, which I calculated earlier. I don't want to write out the whole expression again. IR2 is just basically IS minus this because of Kirchhoff's current law, or I can just do the expression again. And IR3, like we said, is just IS. And the other two, I think you guys get the picture here. And so very easily what I can do is take this, apply Ohm's law, and find the voltages, right? It's just I times R. But what if I want to get them very quickly? So let's say I didn't calculate the currents. How could I find the voltages across all the resistors? A little bit different way. Just to make it, what I'm going to do is move this one up and look at this board again. What is this voltage right here in my original circuit? Which I will push up. One sec. Just give me 1 sec. There we go. What is it in my original circuit? This voltage, VP1, parallel combination voltage. What's that?
IS times RP1.
Yes, okay, so that is true. You're correct. But I'm talking about, like, physically. Where is that in my original circuit?
Where is it?
Yeah, where is it? Which voltage does that represent?
Oh,
Yep, it's just the voltage across that and that, right? It's the voltage across R1 and R2, the same. Okay, and what does this circuit look like? They're in series, which means that the voltage across each one is what? Proportional to the current, yes. But also, two words that I'm looking for. It's a voltage divider, right? It's just a division of the voltage. Vs needs to be split between these three voltages, these three resistors, excuse me. Okay? So what I can do instead of calculating the current times the parallel resistance for each one of these, what I can do instead is just apply the voltage divider formula. Okay? Is that clear? So you can do it either way you want, no matter what. It doesn't matter. It's all equivalent. It's all the same. Okay? Any questions on this so far? It's basically just a recap. We're doing a couple examples of the stuff that we did last time. Everybody good with it? Cool. Now what I want to do is talk about something that you guys are actually going to build in the lab, which is a touch screen. Specifically, a resistive one. Do any of you guys actually have a device that has a resistive touchscreen? Or have you even heard of a device that has one? I wouldn't be surprised if no one's even seen one before. So one example is from a really long time ago, definitely before you guys' time, is the Palm Pilot. That's one. Probably never heard of it. That's okay. Another one that you definitely have heard of is the Nintendo DS. That has a resistive touchscreen and a stylus. At least the old version did. What's a Nintendo DS? Yeah, it's a handheld gaming console. I hoped you guys had heard of that, but I guess not. Basically, so let's, oh boy, all right. So let's go through how this thing works, okay? The idea is, I have some surface, okay? And I want to be able to detect specifically where I touch it. I want to know the position of where I touched this. And the way that the resistive touchscreen works is you actually displace some material and you push it down against a conductor. Okay, so this is some material. There's something between the material and this conductor. This is a conductor. So this is a perfect wire, let's say for now. Okay, so I touch it here, I depress the material, and I touch it against this wire. Is it clear what's going on physically in this scenario? Okay? So how can I use all these circuits that I've learned about, voltage dividers, current dividers, all that, to find where I touched? Just in 1D for now, one dimension. Does anyone have any suggestions? Yeah.
Put a bunch of resistors on the wire that are in series, and then detect what the final division is.
That is a great idea. But what I'm going to do instead, which is equivalent, by the way, is make my material resistive. Instead of having a perfect conductor here, I'm going to make this resistive. So your idea was, your suggestion of making a bunch of resistors along this perfect wire is actually the same. We'll see. So what I want to do instead is I want to model my material as a bunch of wire, or a bunch of resistors. So here's my material. Down here is my wire. Okay? Same thing as before, but now I've drawn an electrical version of what I had here. And what I want to do is, if I press somewhere, let's say right here, this connection is going to make contact with the wire. Okay, now what? So now I've modeled my system. How can I turn this into something that detects where I'm touching? Yeah?
Put a probe on the wire, that way you can know what the voltage, how much voltage is being tested.
Okay, that's a pretty good idea. So let's say we put on my wire, I'm going to attach a voltmeter. Okay? So I'm measuring the voltage of my wire with respect to some ground. I have to measure a voltage difference, right? Okay, so we're getting closer for sure. But what's going on in this circuit? What's this? If I just leave it like this, what's this voltmeter going to read? Probably 0. I actually don't know. Well, so there's no current, so it must be 0. Yeah, you're right. Right now it's 0. If I touch here, it's 0. If I touch over there, it's 0. 0 everywhere. So have I detected the touch? Not quite yet. But we're definitely on the right track here. So what can we do? Can we add to this circuit? Batteries, yeah. Where are we going to put our voltage source? The answer is on the material. Very good. So what happens if I create a potential difference? So I won't explicitly write the voltage source for now. Actually, I will. I'm going to put a voltage across my entire material. Call this voltage the source. And now can I detect the touch? Let's say for the sake of argument, and let's call this ground as well. Again, this is the implied connection, so we're using the same reference for both of our circuits here. Let's say, instead of touching right there, I touch over here. So this part is touching my wire. What will the voltage reading be?
+1. Oh, like +1 vector.
Right, so it'll just be the source voltage. Yep. What if I touch over here? 0, right? Because I'm just measuring the potential between ground and ground. 0. Now if I touch somewhere in the middle, if I label these resistances RR, let's say I touch where I did before, and I make contact right here. What will it be then? A voltage divider, right? Between what and what? In this case, let's say how many resistors do I have? 6. What will it be a voltage division between? What did you say? Could you speak up? Yes, so let's write it out explicitly. So I'm measuring the voltage between this point right here and this point over here, ground. Let me redraw this circuit. Equivalent circuit is the following. I've got some R here, R1 and R2. Here's my V source, where R1 is equal to 2 times R, where R is just one of those resistances, and R2 is 4 times R. Now, which voltage am I actually measuring? You have to jump through some hoops mentally to see exactly which voltage I'm measuring here. Which one is it? Is it across R2 or is it across R1? It's across R2, right? Here's my voltage measurement. I'll call that V out. And V out, as was mentioned earlier, is just 2/3 of my voltage source. Okay? It turns out that I can uniquely determine, at least in these discretized steps, where I've touched it, where I've touched my material. Okay? Is this clear to everybody what we've done beginning to end? We started with a model, electrical model. We figured out exactly how we can detect where I've touched along some line. Okay? Cool. Now what do I do if I want to expand this to 2 dimensions? right? Because a one-dimensional touchscreen is kind of pointless, right? I want to have some surface and there's a conductor underneath it. We'll consider that a perfect conductor. And I want to detect uniquely, I touch here or here or here or anywhere, I want to be able to tell where I've put that touch, where I've touched it. Okay, so how can we extend this idea? Yeah.
Putting that into parallel. So
We could put some resistors into parallel, yes, so that's what we're going to end up having to do.
we will measure the current in each line.
Okay, so you could do that, but measuring current, it turns out, is difficult. In fact, what you do is you actually measure voltage and then extrapolate from Ohm's law what the current is. So let's say we want to do it with a voltage measurement, specifically a voltage measurement on this conductor. So again, this is some material. Down here I've got my conductor. And I'm going to approximate that as having equal potential along the entire thing. That ends up not being quite true because metals do have some resistance, but it's pretty close, right? Especially at low frequencies. Okay, so how can I do this? First, let's figure out a model for this problem, right? So we've got some lattice of resistors. It's my model. Oops, need those two. Looks something like that. This is my approximation for my material. These all have approximately equal resistances. R. Everywhere. And now I want to be able to determine if I touch somewhere, let's say here, for instance, so this is where I'm putting my voltmeter, my voltage measurement. How can I change this circuit? How can I apply some potential to it to determine exactly where I've touched it? Just thinking holistically. Would the same idea work? Yeah?
Could you read the voltage out at the end of each line and then each column?
Yeah, that's a great idea. So the suggestion was, what if I, along each line, measure the voltage, and then measure the voltage along each column, and sort of triangulate, not exactly triangulate, but extrapolate where the touch is. So basically do an x dimension measurement. Let's say this is the x dimension, and this is the y dimension. And basically do the same thing that I did for the one-dimensional touchscreen, but twice, right? So once to determine my x-coordinate, once to determine my y-coordinate. It's an excellent suggestion. So let's draw up a slightly simplified model. Of the touchscreen. Let's say all I want to do is determine a 3x3 grid. Right? So my points are here, 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 these three down the middle, and these three on the bottom. Okay? It's just a simple version. And let's do the same thing that we did before. Let's apply a potential in one direction, and then my voltage measurement will be wherever I make the touch, okay? So let's say I measure the voltage, let's put it right here, right? A nice easy one to start out with. Here's my voltage meter, make the connection down here. What's the voltage that I read there? Just the source voltage, right? Vs. So I can determine that one. But now what happens if instead of, right, that's the easy one. Right? I'm just measuring the voltage across the voltage source. What if I measure in the middle instead? Now what? There's a lot of nodes, right? What's that voltage going to be? Each one of these resistors is R. Well, let's find out. Let's draw an equivalent circuit. Or let's start combining these resistors and try to figure out this voltage. Okay, so here's my voltage source. I'm going to draw it over here instead. Now what can I start doing to these resistances? Let's take those two up in the corner and combine them, right? So I've got some equivalent resistance 2R over here. That's just those two in the top left corner. I have 2R over here, and I've still got R down the middle. I also have this resistance. Let's leave that for now. Let me draw this a little bit bigger. And these I'm also going to combine. So this is still R, R, 2R, R, 2R. Where the voltage I'm trying to measure is still right here, right? So this is my voltmeter connected to that center node. Okay? Now what? This is pretty grim, right? Are there any resistors that are in series or parallel? Anyone have any suggestions? Yes? Go ahead, Nan.
The first two R and the two R, like, are in parallel?
These up here. So you're saying that this resistance right here, this 2R, is in parallel with this resistance, which is in parallel with this resistance? Is that true?
No, sorry, no.
It's a good suggestion, yeah.
The 2R and then down and right, that R, they're in series.
The 2R and then down and right.
The upper left 2R,
Yes?
and then down right.
This one?
No, like if you move your left hand like 1/5 to the right.
What? 1/5 to the right.
They're like
One of the center R's.
The center R's, this one. Oh, these guys.
those are in series.
So you're saying that this resistance and this resistance are in series?
Actually, not mine.
No, that's not true either, right? There's nothing left, yeah. Oh yeah, let's do nodal analysis. Let's not. There's so many nodes in this circuit, right? This is a hopeless number of nodes. Not hopeless, but okay, never hopeless. You can always do nodal analysis, yeah.
You have a symmetry between all the two R's and the R's. What if you can somehow fold it 4 ways so you one box of just 2R, R, and R.
So I have some level of symmetry in my circuit, right? And the suggestion is, can you collapse the 4 R's? Well, let's just say, I'm going to claim that this voltage over here on this left node and this voltage over here on this right node are the same. And again, I'm just going to claim that. I'm going to call this one Vx and Vy, and I'm going to say these two are the same. They're the same potential from a symmetry argument, and we'll see if that's true. If we make this assumption, something will break along the way if it's not true. Okay, so this is voltage Vx, this is voltage Vy. If that's the case, if these two voltages are the same, what does that mean about my circuit? It turns out that this one, I believe, is the same as well. If I've got a voltage here Vx and a voltage here Vy, and those two are equal, so Vx equals Vy, what does that mean? So they're not in parallel because there's resistors in the way. What does that mean about current flowing from one side of my circuit to the other? The same. If there's no potential difference, is there any current? No, there's no current. Which means that what I can do, if these are the same, is basically just get rid of these resistors down the middle. So I'm going to draw, so if this is the case, if my assumption is true, I'm just going to get rid of those resistors. And now my circuit turn them into open circuits, there's no current. Here I've got 2R, R, 2R. Just like this. Potentials are the same, so there's no current, and those resistors they may as well not even be there. Yeah?
But can't current from Vx go to the right-hand slope, go up or down?
So I'm claiming that these three potentials are all the same. Is basically what I'm saying. Yeah, all three of them. And so now, what's the potential right in the middle? It's just a voltage divider, right? Specifically, a division by 2. So if I've got some source voltage Vs, it's Vs over 2. Okay? But if this is true, that basically tells me if I've got this two-dimensional grid of resistors from before, and I apply a voltage from the top and from the bottom, all I can do is tell which row I'm touching. Right? I can either measure the top one, middle one, or bottom one. I can't actually distinguish between left and right, right? Because of the symmetry in the circuit. So now let's get back to Isaac's suggestion. What if we do first a measurement in so in this case, the y direction, then let's do a measurement in the x direction. How can we do that? How can we actually perform that measurement? I'll give you a hint. There was a circuit element that we talked about last time, quite briefly. I'll just remind you. A switch. Okay, looked something like this. Now the potential across the switch I'm going to define here. The current through it I'm going to define like this. Okay? If the switch is open, what is the current through the switch? 0. Voltage could be anything. Just a open circuit, right? If it's short or shut or closed, the voltage is equal to 0. It acts like a perfect conductor. Just like a light switch, if I have it in the off position, there's no current, so there's no light. Okay? And if it's in the on position, there's no voltage across it, so all the current is going to go through my light bulb. Yep. Clear, everybody? So how can I take advantage of this in my touch screen? So again, I'm going to draw out the entire resistive grid. And I want to make measurements, yeah?
2 batteries, one that goes when the switch is open, one that goes when the switch is off.
Yeah, let's just do that. Let's do it with 2 batteries. So this is not big enough. That's fine. So in one case, I want to take a battery or a voltage source, and I want to hook it up between these 2 terminals. And like we showed earlier, that basically gives me the Y dimension of my touch. And I want to put another battery or voltage source. Oh, this is going to get like this. I realize that this is a little bit confusing, but basically I've taken my batteries. One is going to tell me the Y dimension of my touch. One is going to tell me the X dimension. Okay? Is that clear to everybody why the X dimension works? Basically take the same analysis that we did for the Y dimension, turn it 90 degrees to the right or left. Okay, is that clear? And now we incorporate, because if we just had these 2 voltage sources on all the time, it wouldn't really tell us much. So now what we want to do is put in series with these voltage sources a couple of switches. Right, that way, when this one is short, I can make my X dimension measurement. And this one is short, I can make my Y dimension measurement. Okay? And that's how we can make a 2-dimensional touchscreen. And you guys are actually going to build this exact circuit in the lab, and it's actually a pretty fun lab. You get to solder as well. Cool. So any questions on this? By the way, yeah? Excellent question. So the way that you'd measure the voltage in the lab, you can use a voltmeter. So that's just a piece of equipment that you have. And you'll actually, I think you'll get to play with that in lab on Wednesday and Thursday. You can also use, most microprocessors, like the one that you have, actually has what's called an analog to digital converter, which takes an analog voltage, like the one that you'd generate with this kind of circuit, and turns it into a digital code. You've actually already used that. So that's what you use to measure the voltage across the resistor in the imaging lab. It's an analog to digital converter, yeah.
How do we make sure the single R's in the middle that have that they have no voltage, they have no current at all in them?
Yep, so in reality, these 2 resistances won't be exactly the same. And so you can't actually ensure it, but it will be pretty close. Yes?
Why was the answer to that one VS over 2 again?
Ah, yeah, okay, so if we look only at this branch of the circuit, what this looks like is a voltage source with 2 resistances R and R, which is just a voltage divider. And the formula is R over R1 plus R2. In this case, both the resistances are the same, so you get the source voltage divided by 2. Great. Any other questions on this? Cool. There is one more circuit that I think we have time to analyze, and it shows up on your homework. So you might want to pay attention. And it's what's called a Wheatstone bridge. It's actually a fairly famous circuit. It takes advantage of a very similar thing that we saw in the touchscreen. Looks like the following. This is a source voltage with these 4 resistors. Typically what we do is we measure the voltage across these 2 terminals. So I'm going to call this V out. Okay? There's a couple different ways that we can find V out here. So let's just do it for practice, right? Let's do it pretty much every way. That way we can really consolidate all the different ways that we've learned to analyze circuits. So just to summarize, what's one way we can do this? One way to analyze a circuit. Nodal analysis, we certainly could. We could do it with nodal analysis. What else did we learn? Parallel and series combination of resistances. And that way we can simplify our circuits, make them easier to solve. And we can also do voltage and current dividers. We'll see that solving circuits comes down mostly to pattern matching, actually. So you just recognize different pattern circuits, and you just repeat the same process. Yeah? Yeah, you're right. Okay, so let's combine these into, these 2 together are the other way we've learned of analyzing circuits. That's actually a pretty good point. Okay? Do you guys want to do it with nodal analysis? Would you like more practice with nodal analysis, or would you prefer it if I did series parallel way? Or both? I think we have time for both. Both. Sure, let's do both. I was saying a lot of circuits analysis pretty much comes down to pattern matching. If you talk to old circuit designers, for whatever reason you're talking to one of them, they'll call it intuition. So you sort of look at a circuit and you say, I know all the voltages in this circuit. Truth is, they just practiced a lot. Okay, so let's do nodal analysis on this circuit. So first, nodal analysis style. R1, just redraw the circuit. Okay, so the first thing that I want to do in nodal analysis is identify all of the nodes. So first off, how many nodes do I have in my circuit? 4 nodes, right? Is that clear to everybody? I'm going to write them out. So we've got this node up here, this node right here, this node here, and this node down here. Cool. So those are the 4 nodes in my circuit. If you guys are having issues with identifying nodes at all, please come to office hours. Like, it's a little bit subtle because we make a lot of assumptions implicit in when we define these nodes. Meaning everything that's connected by a wire is the same potential. Okay? Now I'm going to label these. U1, U2, U3, U4. Now what's my next step? I have to define a ground, some potential that I just say is ground. Now, I would probably choose this one, but you can choose whatever you want, okay? I'm going to choose this one because it makes things easy in the end, or later on. And now what? Now I sum the currents at every node. So let's do that. For each one of these, and this is just a personal preference thing, like to sum all the currents out. So I'm going to call this one I11, I12, I13. Okay, so I11 is going left, I12 down, I13 to the right. So the sum of the currents at node 1 is equal to 0 here. So this is the sum of the currents out, is equal to I11 plus I12 plus I13, right? Now, what are each of these currents in terms of the potentials? Node's law, or Ohm's law, excuse me. What's I11? We don't know yet, right? It's the current from a voltage source, which could be anything, okay? We don't know it. Let's just leave it as a variable, call it I11. Now, what about I12? U1 minus U2 divided by R1. Right? This current is going to be the potential at this side of the resistor minus the potential at this side of the resistor divided by the resistance. Okay? Is it clear to everybody? And now let me just do the last one real quick. U1 minus U3 divided by R2. This sum is equal to 0. Good? Good. Let's do this for U2. Now this one, again, I'm going to do the currents out. I'm going to call this current going up I21, and this current going down I22. Okay, so I know that sum out is equal to 0, I21 plus I22, which in this case is U2 minus U1 divided by R1. That's this first current. Plus U2 minus U4 divided by R3. Now, what's U4? 0. Why? Because I made it 0. I chose this to be my ground, so this is 0. Cool. Okay? Is this procedure clear to everybody? Do you want me to continue, or do you want me to do it the fast way? I think we have, so this is, yeah, I have time. Lots of time. So let's continue with this. Some of the currents at node 3 are what? Let's say I've got an I31. I'll draw them up in a second. Let's call this one I31, this one I32. Okay, so I31, it's far away from me, so someone's going to have to help me out here. What is this? U3 minus U1 over R2, thank you, plus U3 minus U4 over R4, thank you. And again, U4 is equal to 0. Why? Because I made it 0. Okay, now we've got this last one at node 4. Again, the currents out are equal to 0. And here we've got current, let's call this I41, I42, and I43. So all of them are going out. 41 to the left, 42 up, 43 to the right. And again, I'm going to need help here. What's this equal to? Negative I11. We'll talk about this in just a second. Let's get the easy ones here, the Ohm's law ones. U4 minus U2 over R3 plus U4 minus U3 over R4. Great. And again, U4 is equal to 0. Now let's get back to this minus I11 for a second. So this current, I41, I defined going in this direction. So I can draw it going like this. This is I41, right? Is that clear to everybody? So it's the same current in the entire branch. But I also had this current that I already used, I11. That one's going the other way. This is I11. So they have to be, one has to be equal to negative the other. They're just the same current going in different directions. Okay, and that's why I wrote negative I11 there. I could have done I41 as well. It makes no difference. Okay? Now what's the other equation that I have? What else do I know about the potentials in my circuit? Yes. The answer is, I know that U1, excuse me, minus U4 is equal to Vs, right? That's my source voltage. Okay? And so now what I can do is rewrite all my equations in terms of the things that I know and then just solve them just like I would any other system of equations. Okay? Is that clear to everybody? So that's why it's so methodical, right? There's no way you can mess it up. Never do you make any assumptions about series or parallel. Never do you make any assumptions about voltage division or current division. You just sit down and grind out the answer. Okay? Now what's the alternative way of solving this circuit? The sort of intuition approach. So let me draw it up again, just to make it clear. This is my circuit. Source voltage, R1, R2, R3, and R4. If I just look at one branch of this circuit, let's just say this one, right here. What does this look like? The circuits that we've solved already. They're in series, yes. And which one, we've only really learned two circuits. Which one is it? It's a voltage division, right? So if I label this node right here, Vx, say, Vx is going to be the source voltage, Vs, times what? R2 over R1 plus R2. Right? And there's an assumption that I made in this, because a potential at a point doesn't really make sense, right? So I've taken the potential difference across this resistor right here. That's what I'm calling Vx. Okay? Now what about this one right here, Vy? What's that? Yeah. Yeah. So the answer is, again, just a voltage divider, right? Okay? So these are my two expressions for the two voltages on each branch here. Now what if I want to find, from my original problem, V out, meaning the voltage between, rather than Vx to ground, Vy to ground, I want to find the voltage hold on one sec. I want to find this voltage V out. What is that voltage? Vx minus V out. Sorry, minus Vy. Is that clear to everybody, why that is? Sorry? Could I explain it? Yes, I can. So there's two different ways of looking at it. One, you can look at it from a Kirchhoff's voltage law perspective. The other way you can look at it is the following. So implicit in these voltage expressions is a subtraction in potentials. So let's say I define this, just like I did in the nodal analysis problem, as some potential related to ground. And I'm going to say Vx is equal to, I think I labeled that node 2. Node 2 minus 0, right? Which is the potential plus minus. Similarly, Vy is U3 minus 0. Same thing. And so if I want to find the potential between these two, it's just U2 minus U3, okay? And because of this 0 present here, it's equivalent to saying Vx minus Vy. Okay, good question. All right? So that was a much faster way of solving it. The nodal analysis was a lot. I didn't even want to solve that system of equations. This way, I could just look at the circuit and pretty much write the answer down right away. Okay? Is it clear how I did this to everybody? Oh, I went over time. I'm sorry. Okay. Good luck on your midterm. Have fun a little bit. Try to. I'll see you all tomorrow.